Good morning, we are Cristian Gomez and Camilo Salcedo, and we will make the presentation of the approach titled Battle of the Leakage Detection and Isolation Methods and Energy Method Analysis using Genetic Algorithms in behalf of Water Supply and Sewers Systems Research Center, Ciacua, from Universidad de los Andes in Colombia. In water networks, leakages can occur in junctions between pipes, breaks in the pipes, or accessories that form part of storage tanks and compensation tanks. In addition, leakage can happen due to the movement or settling of the ground, traffic, or poor quality materials. When the behavior of leaks is analyzed, they are dependent on the demand, which varies along the day. In the first graph, the fluctuation of pressure along a day is depicted. The effect of leakages over the pressure management are described in the graph as well. On the other hand, graph 2 shows how a greater demand results in an increased pressure, which causes leaks to increase too. The methodology used to solve this battle required the use of a calibrated hydraulic model for the network. Then the leaks are simulated in the nodes through the emitter accessories, where the flow rate from leakages is assumed to be a function of the pressure at that point, as indicated in the emitter equation, as shown in the equation number 1. The anomaly detection analysis started with the SCADA dataset collected between 2018 and 2019 at a 5 minutes intervals. Initially, we analyzed the different behaviors in existing pressure data to identify the possible relation between anomalies and the occurrence of leaks in the system. An example can be seen on the figure, where there is a variation of pressure near 500 seconds. This was the first step to focus our analysis in the pressure behavior between the model and the SCADA data. The modeling procedure was performed using MATLAB and EPANET. MATLAB was selected due to a high computational efficiency for managing big volumes of data. On the other hand, EPANET was chosen because it is a well-known hydraulic simulator capable of performing water distribution system analysis in an extended period. To perform the simulations required for the genetic algorithms, MATLAB communicated with EPANET through Programmer's Toolkit. First, the individual's information was sent to EPANET, who performed the hydraulic simulation. Then, the hydraulic results were sent to MATLAB, who developed the operations.
The implementation process consists in the following steps. First, anomaly detection analysis was developed. Different signals from SCADA 2019 and EPANET model were quantified using root mean square error. Then, if this performance measurement was greater than 0.2 for any sensor, in any instant of time, a leakage was identified in that location for the same instant of time. Otherwise, no leakage was identified. At this point, it is important to highlight that anomaly detection tends to identify leakage between a continuous time slot. So, to avoid identifying the same leakage more than one time, a restriction was implemented. So, two leakages must be separate at least 2 weeks. After this process, 8 leakages were identified from 2019. For each leakage location, the genetic algorithms was implemented with 300 generations and 60 individuals. The first step of the genetic algorithms is to create an initial population in which there are possible solutions to the main problem. Each individual has 4 specific genes that compose a chromosome that describe it. These characteristics are the number of individuals, node list, X and Y coordinates of each node, and leakage time. These genes describe the possibility of finding a leak in the pipe. To perform the selection process among the generated individuals, it was necessary to adopt a classification function that allows quantifying the similarity of the individuals with the leaks registered in SCADA. The pressure signal record were implemented as a selection method between the individuals and the SCADA record, due to the fact that present more prominently fluctuations caused by the presented leakage than other registered variables. In other words, it was compared the pressure signal between the SCADA records in each of the sensors and pressure signals estimated by the genetic algorithms. For these comparisons, the root mean square error was selected because it has a low computational cost and is an evaluation criterion used in a variety of cases of autonomous supervised learning. Therefore, the objective function implement consists of minimizing the root mean square error combined with a factor that disqualifies the individual in case of being out of the acceptable time range. Based on the objective function, a score is assigned to all previous generated individuals. With this process, they are classified from the best to worst and then select the top 40% of the population to go through the mutation and recombination process. The following figure shows the A leakage identified for 2019. After analyzing the results, it is concluded that leakage detected located in Zone A are mostly concentrated in two groups. The first group is located near the tank that supplies Zone C, northwest of the network, for the period between April and June. The above indicates a correlation between the leakage and the time of installation of the pipes. Additionally, the concentration of leakage reflects a significant deterioration in the sector. The second group occurs in the area near Reservoir Number 1, in the northeast of the network, for February and September respectively. Therefore, the sector is progressively affected by degradation throughout the year.